I would like to thanks to the organizers and especially the convener of this conference. Yeah. So the topic for today's presentation is challenges and opportunities in indigenization of hydrogen fuel cell technology for mobility and power generation applications from an Indian perspective. So in the morning session, 2 morning sessions, we have seen the talks mainly from the perspective of government policies, government initiatives, how the hydrogen penetration or the efforts required to increase the hydrogen penetration in terms of its generation, storage, transportation. Now, I think in this session, we are going to see a very important side of this technology, that is the implementation part of it. So I think this is the first presentation in this session, which is going to focus on the complete design development process. So I will take you through what I can say, a small kind of a journey. So you will come to know what are the kind of things at my organization we are doing in this technology. So myself, Sushil Ramdasi, he has already introduced the session chairman. I'm in charge of a powertrain design at Automotive Research Association of India. Yeah. So this is the overview, or I can say the glimpse of today's presentation. So quickly we will see what's happening in present scenario. Present scenario of what? Powertrain. What's happening in present powertrain scenario? Okay. Now, because of the time constraint, I will not talk on the ecosystem and supply chain issues related with it. Then we will see the need for electrification, hybridization, and global roadmap for sustainable mobility. Okay. Then what are the potential segments from hybrid electric, EV, and FCEV from Indian perspective? I'm just going to touch upon it. The bold words, what you are saying, that is my main content of today's presentation. Then we will see what kind of work we are doing at ARAI, because we are transforming from conventional powertrain to the future mobility. So through EV, rather it was started with the hybrid electric vehicle first, electric vehicle, then fuel cell electric vehicle, the case study, the projects what we are doing, followed by the advanced powertrains which are required for the fuel cell electric vehicles. Hydrogen generation and storage. So I will just touch upon the storage because so many people have already talked on the generation part. Then what are the fuel cell based power generation? Just a quick overview, and then we will summarize. Yeah. So you know that in conventional powertrain technology, the government of India implemented or adopted Euro norms in year 2000. And right now we are in Euro 6. So in this last 20 years, there was a huge revolution in conventional powertrain technology. Now, when we started from Euro 0 to Euro 6, there were key drivers, such as to meet different norms like Euro 2, Euro 3, Euro 4, Euro 6, followed by there were challenges to improve the fuel consumptions, lower CO2 emissions, high specific power, improved NVH, etc. But while focusing these drivers, there were so many challenges, and the main challenge is that you can see that the cost of engine technology, or the difference between the cost of engine technology between Euro 4 to Euro 6 is almost 25 to 30%. So that is the biggest challenge, challenge number one. The second challenge, even we have implemented Euro 6 technology, the CO2 emissions are of the order of 120, 140 grams per kilometer. So by looking at the Paris Agreement, what we have signed, that our endeavor should be reduce this temperature, or it should not exceed 1.5 degrees centigrade. So we have to bring down these CO2 emissions less than 100 grams per kilometer. So even that is not possible with conventional Euro 6 technology. And third one, the fossil fuel depletion. So there has to be an alternate to replace this fossil fuel. And that is the reason now there is a change required rather than upgrade the technology. For last 100 years, IC engine technology, transmission technology is there. So in the last 100 years, we have optimized its efficiency to the best point. But now there is a need to change the technology in terms of electrification. So in ARAI, in present powertrain scenario, we have developed all engines from concept till serial production. So these are some of the engines complying the latest emission norms for off-highway applications for the European customer. In last 10 years, these are some of the engines we developed for various customers in India, major OEMs, in all kind of segments such as tractor, power generation, gensets, passenger car segment, then off-highway segment such as construction equipment vehicle, heavy-duty application. Because many people know ARAI as only certification organization, and that is the reason actually I want to take this opportunity to give the message. So it's a premier R&D organization of India, government of India. And when we say powertrain, it's not only engine, it comes along with the transmission. So this is the latest transmission, 7-speed automated manual transmission for a hybrid electric vehicle architecture. That is the P3 architecture. So we developed P3 hybrid electric vehicle architecture, and we demonstrated 24% fuel economy on chassis dynamometer. Then comes the axle. Now this is a typical example of a 4-wheel drive front axle for a tractor application. Now you may thinking why I'm showing this. Because all these things are required to develop the advanced powertrains for a fuel cell electric vehicles. So this is the background for that. Yeah. So now just to summarize the first part of the presentation, we have seen what's happening in the conventional powertrain and where are we. So now just to summarize, there is a fossil fuel depletion, need to reduce import crude oil percentage, stringent CO2 emission norms, it should be less than 100 grams per kilometer, and from Euro 4 to Euro 6, you can see that there's a 25% rise in the overall cost of the product on serial production. Now Euro 7 is coming, so you can see the rise which is exponentially going, and that's the technologies become costlier and costlier. Even with that, we cannot meet the main two challenges, CO2 reduction further and global warming temperature. And that is the reason now electrification is must after Euro 6. And that electrification comes in threefold. The first one comes with a hybrid electric vehicle, followed by electric vehicle, followed by the hydrogen fuel cell electric vehicle. So this is the global roadmap. You can see on the x-axis from 2010 to 2050. The good news is that the IC engines are not going to die. They will be there 2050. All technologies will coexist by 2050. IC engines will be there in the form of biofuels. They will be in the form of hybrids, okay? But not as a pure IC engine. Electrification is must, followed by hybrids, plug-in hybrids, strong hybrids. Then next segment comes pure electric vehicles, followed by hydrogen fuel cell electric vehicle, but in certain decided segments. Which those segments we will see in the next slides. So once we studied this global roadmap, then we decided from Indian perspective where we should focus. So this is the segmentation. So I will just concentrate on the fuel cell electric vehicle technology. So we foresee that the heavy commercial vehicles and buses, that is the intercity applications, these are the right candidate to convert electric vehicles into the hydrogen fuel cell electric vehicles. There are some definite reasons we will see in the next slides. So to start this journey, few years back, 5 to 7 years back, we started working first to develop an electric vehicle by ourselves. So this is a complete front loading or V approach, V loading approach. That means development of electric vehicle through model-based simulation techniques, followed by software in loop, processor in loop, component in loop, and hardware in loop simulation techniques. Right now in India, the electric vehicle segment is highly unorganized in nature, okay? So in order to streamline that, this is the complete tool chain, the competency which is established. And you can see that we have demonstrated a range of 120 kilometer with a battery of 14.7 kilowatt hour as a lithium-ion battery. So this is the first product what we developed. With that experience, we developed a complete electric vehicle, okay? Same process, but only thing, the steel superstructure we replaced with aluminum superstructure, and we reduced 700 kg weight, okay? So that has given an add-on advantage to place the high energy density of the battery, or even in future, we can place hydrogen storage cylinders and the fuel cell. Okay, now coming back to the today's topic, the fuel cell technology, which is a power source for the future. So here we are going to see the fuel cell applications for both segments, that is for mobility as well as for the power generation sector. So there are some youngsters, that's why actually I added some of the basic fundamental slides. I will not go through into this, but you can see over here Centrally, there is a thin polymer membrane of 30 microns. It acts as an electrolyte. On left-hand side, there is a catalyst which is pasted. It serves as anode and cathode. Then there is a gas diffusion layer followed by the bipolar plates. So the hydrogen entering side is called as the anode, and the oxygen or air entering side is a cathode. You can see the reactions. The open circuit voltage will create once we supply the hydrogen and air on both sides, but when you connect it to the load, then there is a voltage difference takes place and the current will start flowing. And that delta V comes in the order of 0.6 to 0.8 voltage in practical world. So what I have shown is a single cell. If you arrange these cells in series and stack, you can create the fuel cell stack. So this is a typical 3 kilowatt, 48 volt fuel cell stack, just how it looks like. Now, one important statement I want to make here, electric vehicles and fuel cell electric vehicles, if we see, compare, they are not competitors to each other. Basically, fuel cell electric vehicle is an extension of the electric vehicle. Rather, it complements to the electric vehicle. In terms of what? There is a potential to reduce the size of the battery, cost of the battery, weight of the battery, because there is an onboard fuel cell which can charges the battery. Also, it can give the direct power to the wheels. So this is the picture that shows that how EV is converted into the FCEV. Now, when we say fuel cell, so there are basically three different terms we use. One is called as cell, second one is called as stack, and third one is called as the fuel cell engine. The first picture we have seen is a simple cell. Then we have seen a stack, means assembly of cells makes a stack. And when stack is connected with other auxiliary components, such as on anode side and cathode side, we call it as a balance of plant, which supplies hydrogen and oxygen, which supplies humidification, okay? So with that, a complete fuel cell engine we can manufacture, and this is a typical fuel cell engine, 100 kilowatt. It's for a bus application, how it looks like. So this is the technology what we want to develop in India as an indigenous technology, and that is the potential future for us. So from Indian perspective, this is the complete market spread. So you can see that the segmentation, that passenger cars and three-wheelers, passenger cars which will ply within city, we call it as an intracity, okay? These two, or even intracity bus, means which ply within the city. We can apply a low power fuel cell. For example, Nissan Leaf, which is launched in Brazil, it's a 30 kilowatt rated power induction motor, and they have 5 kilowatt solid oxide based fuel cell, which is fueled by an ethanol, okay? So this is called as a range extender. So with reference to the power of the motor, the power of the fuel cell is just to charge the battery, okay, and just to give the range. So in that case, it is not giving direct power to the wheels. It has to give it, but the magnitude is very less. Then the next segment comes, that is the heavy commercial vehicle. Here we see the maximum application of the fuel cell. Reason, for example, we want to travel 500 kilometer plus distance in a single charge, 500, 800 kilometers. Then we require 300 kilowatt hour battery, okay, maybe of 600 volts. It will last maybe around 300 kilometers. Then the entire battery will get depleted. Then you have to charge it. Now, even if you do with a fast charging, minimum 4 hours. And now just see if it is a bus application, passenger with passenger, 4 hours we cannot afford. So that is the reason, in that case, we can have a fuel cell roughly, if 300 kilowatt hour is your battery size, then around 100 to 120 kilowatt fuel cell is sufficient. And with that combination, 300 kilowatt hour battery can be toned down between 150 to 180 kilowatt hour. So with this combination, you have reduced battery size substantially, less than half, which reduces cost, weight. And secondly, the fuel, since there is a fuel cell, the depth of discharge is not from 0.9 to 0.2. It is in a very narrow control, 0.9 to 0.6, which improves the life. And you can imagine what is the cost of the 300 kilowatt hour battery. Of course, there is a cost for the fuel cell also, but it's like a chicken and egg situation right now. So once the serial productions will start, I think the things will become better. Forklift also find a very good application for a fuel cell, followed by tractor. Even there are a lot of electric tractors are picking up. And the problem with the electric tractor is that the duty cycle in field, okay, it sucks the battery like anything. Means the tractor has to work, it's expected to work for 8 hours, okay? But the battery, the maximum battery you can accommodate, whatever kilowatt hour, it only runs for 2 or 3 hours, okay? So there, the fuel cell makes a sense. So this is a complete tool chain and resources available at our end, and the total process what we follow to convert existing EV into the FCEV. So first, range estimation of the base electric vehicle, followed by high fidelity mathematical model, and then calibrating that results with base range, then creating high fidelity model of fuel cell, and then integrating with the base EV, and then do the sizing. Then you have to decide whether the fuel cell you want to act in a parallel mode or in series mode, okay? And then you can optimize the size of the fuel cell to get the desired range. Once that is done, you can package it from balance of plant and fuel cell stack point of view. You can again put it on a chassis dynamometer, okay? And then you can deploy your control strategy. The control strategy is the heart of this complete thing. When to operate battery, when to operate the fuel cell, when to operate both, when to charge the battery from the fuel cell. So all these things we call it as a control strategy. And then testing of the fuel cell on stack, followed by the hydrogen cylinders testing in a different test facility. So the same thing what I have just described, it is written. But we can see that while transforming from ICE to EV, from EV to FCEV, okay, we have to think how this transformation be smooth. It should not act as a disruption. It should create the opportunities, okay? So this transformation should be feasible and it should create a sustainable business scenario. So there are a lot of opportunities such as R&D to develop indigenous fuel cell, to develop indigenous stacks, to develop indigenous controller, ecosystem, supply chain, testing and certification, regulatory framework. All this will fetch new business perspective, scenario, and opportunities in India. So this is the controller development, what I mentioned. This is the high fidelity model of electric tractor, what we are working with a forward approach. We have developed our own induction motor, PMSM motor, field orientation controller. It's not just using a direct tool chain from the MATLAB Simulink, but the complete voltage flux linkage equations we have implemented, tested, and validated. Once that is done, then you have to model a complete fuel cell electrochemistry. And this is a typical inputs which are required for that. And this is the fuel cell polarization curve, which is experimentally validated. Once these both models are ready, high fidelity model of the electric vehicle, high fidelity model of the fuel cell, then you can integrate it. But before that, you can test it, the polarization curve, power and efficiency curve. And then you can make the FCEV complete model to design a control strategy. So this is just a small glimpse of the control strategy which goes into it. Now, another opportunity from indigenization, when you indigenize the fuel cell, there's a lot of, first very important thing, the costly material part is the membrane that everybody knows. So this is a polymer electrolyte membrane. Right now there is no option. We have to import it, followed by the catalyst. Right now, again, this is a platinum catalyst, but a lot of work is going to replace this platinum by nanoparticles. I think 90% platinum reduction is already there. Still 10% is there, but which is the costly element. Gas diffusion layer, bipolar plates. These are the balance of plant components. There are so many companies are approaching us to help in design and develop this balance of plant. This is the typical hydrogen recirculation pump. And finally, even there are requirements of indigenous test centers to test these fuel cells. It's a very, very expensive element. I think Dr. Panda is already here, so I think you might be aware the kind of cost goes into all these kind of projects and the typical investments which require for that. This is the work what we did with one of the US-based university for development of 3 electric buses for New York City application, okay, from EV to the FCEV. So we got direct exposure to work into these projects, which we used to convert existing electric vehicle to fuel cell electric vehicle. Range extension, 60% only, because there is no place to accommodate higher storage cylinder, and that too it is a type 3. We cannot go for a type 4. So space is a constraint. This is a cargo. This is an electric tractor, which you have converted into the fuel cell electric tractor. Considering the rotavator operation, which is the toughest operation or the full load operation, 8 kg hydrogen is sufficient to run that. So we have demonstrated it. Right now, through simulation, the prototype buildings of all these projects are in the process. Similarly, we are participating in the tenders for the railway. So the basic groundwork we have completed. So apart from fuel cell, this is another challenge. These are the type 3 cylinders, 350 bar, aluminum cylinders with the carbon composites. Now we require type 4 in future, where the carbon composites are replaced by the polymer. And this is the last slide. Now, whoever is developing electric vehicle, we always recommend, suggest, rather this is the latest trend across the globe, make EV through electric axle route. Conventional way is like just replace IC engine, put electric vehicle, keep transmission, propeller shaft, differential. Second modification, reduce number of speeds of the main transmission, maybe 2 to 3. Keep propeller shaft, differential. Okay? Third option, go for a single speed. Again, remaining drivetrain remains same. But here, you can have a complete electric motor integrated into the direct axle. But again, there are two ways of making it. One is called as the conventional one, which you can see over here. And the second one at the bottom, it is called as a power distribution unit. The complete power electronics, motor, the transmission housing, and the cooling system is integrated. So it becomes a very compact. Okay? There are no high voltage cables. There are bus bars, which reduces I2R losses. So this kind of technology right now we are working. So if anybody want to convert EV to the FCEV, we strongly recommend to go with this. Reason is that since everything is focused on the axle, you will get a lot of space in the vehicle to place the battery, to place the hydrogen storage, okay, and to maintain the CG of the vehicle and structural dynamics becomes very easy. So the second application is a power generation application. Only one slide is there. So in power generation, we foresee solid oxide based fuel cell for a megawatt kind of application. Rather, and maybe up to 1 megawatt, you can use hydrogen PEM fuel cell. But above 1 megawatt, it's better to go with solid oxide based fuel cell so that you can use pipe CNG, ethanol, methanol as a fuel, and you can generate hydrogen on board through reformer. And efficiency is also very less. It's a stationary application, 60% as against conventional PEM. But yes, in India, we have both options. But if you want to go even for a megawatt, 1 megawatt application, it's advisable to go with the fuel cell power generation associated with electrolyzer. So it should generate hydrogen there itself. Otherwise, the kind of hydrogen which is required even to operate 1 megawatt hydrogen fuel cell, generation, storage, transportation is a big question mark. So just to summarize, now this is overall summary, not specific to the fuel cell point of view. From Indian perspective, ideally we should have followed the roadmap of Japan and South Korea, but we have followed the roadmap of China. Okay, we directly jumped, okay, from ICE to EV. We skipped the hybrid electric vehicle route. Ideally, we should have started with that, which would have given 20%, 24, 25% fuel economy, okay, which we call it as a low-cost parallel hybrid. Followed by, then you can go with a larger battery, we call it as a plug-in. Actually, we should have gone with that, but I think that option is totally ruled out because the GST segment, what we have Government of India has put, it's in the luxury segment. Phase 2, now there are a lot of electric three-wheelers are running. Electric passenger cars are increasing. So we can use a small, like 3 kilowatt, 5 kilowatt, what Nissan has used, kind of PEM or SAFC, so that we should not depend on the charging infrastructure till it gets matured. Followed by, you have to quickly work on the high temperature PEM equivalent fuel cells, okay, so that CO tolerance, which need to be improved. And also, we have to reduce further the platinum content by replacing it with the nanoparticle based technology. there is a high potential for implementation of hydrogen PEM and solid oxide fuel cell in power generation applications. Huge potential, and there is immense opportunities. Now, when we say EV, FCEV, okay, there is a common thread, and that common thread is nothing but the electric drive. Okay, so we just can't say that hydrogen, hydrogen. You have to see a complete total system. Then you will get a complete total control on the cost and the efficiency. So you have to do indigenous development of motors, motor controllers, power electronics, battery, BMS, AMT, DCT, low cost PEM equivalent FC. That's what I said, high temperature fuel cells, SOFC, etc. from Indian market or for Indian markets. So a lot of talent is available over here. So we have to upgrade those skills. We have to give opportunities to all those youngsters so that I think within 8 to 10 years, I think the percentage of EVs and FCEVs will increase. Thank you.
Thank you.